when we try to convert into scientific notation, we first need to determine how many, which of these digits are significant. So when I look at these significant digits, it's 281. The multiplier is never going to be part of the significance. That's always non-significant. Here, I don't include this trailing one, the leading ones. I start at the first non-zero, 763. I pause at the last non-zero, and then I look to see there is a decimal point, so I'm going to continue to underline all the way to the end. So I have 5 significant digits here. Here I start at the first non-zero, I go to the last non-zero, I pause, I don't see a decimal place, so I'm going to lift my pencil and I will have determined. So my significant digits here, I'm just going to convert this part. Since that's the part, this is already expressed as a power of 10. So I'm going to take the 281, and here I have 76300, and here I have 3152. Okay, now I have to express it as a, with the decimal point after first number. So 2.81, and this would be 7.6300. This would be 3.152. And next, I have to decide how many places it's going to take to get it to this position. So this would be 1, 2. So I say times 10 to the 2. To determine the sign, whether this is plus or minus, I look at this. This is a big number, bigger than 1. So I need a positive exponent. So this would be plus 2. And then I still have the times 10 to the 6. Note that now I can add the exponents. So this is now 2.81 times 10 to the 8th. If I look here, okay, I'm going to have to get this decimal point from where it's implied. This is the implied to start. And here it's going to be here. Oh wait, sorry, this one's not implied. This one's implied. This one's here. I missed that. Okay. All right, so I'm just going from here, 1, 2. So also times 10 to the 2. However, this is a small number, so I need a negative exponent. So that would be a negative exponent. And here, I have to go from 1, 2, 3, 4, 5, 6, 7 places times 10 to the 7. And this is a big number, so I need a positive exponent. So that'll be a positive 7. And that's how we convert into scientific notation. Looking at this problem, this is a little bit tricky because when we say least precise, how many significant figures? So I want to know quantity of sig figs in the least precise. Well, again, how we measure least precise depends on the operation. If I'm doing plus minus, least precise is largest value of last significant place value. And we mean largest, we mean leftmost in the placed value series. If I'm doing times or divided by, least precise is smallest quantity of significant figures. Well, since this is asking me how many, it's asking me for quantity, so this would be question 1. I'm going to use this method. I'm going to assume it's the fewest number of sig figs. So it's a little bit of an implied situation in this, the way this is worded, because I don't see an operation, but this is sort of presumably I was going to add or subtract these, or no, multiply or divide these. Okay, so first I start at the first non-zero. That's the 1. I go to the last one. I pause. I look for a decimal point, and I see one, so I go to the end. Here I begin at the first non-zero, I underline to the last non-zero, I pause, I look for a decimal point, I see one, I continue to the end. I start at the first non-zero, I continue to the last non-zero, it's the end of the number, so I'm done. Now I count how many I underlined. 1, 2, 3, 4, 5. 5 sig figs. 1, 2, 3, this one's 3 sig figs. 1, 2, 3, 4, 5, this one's 5 sig figs. So this is the fewest. So this would be the least precise. And we get 3. What is the place value? So now this one is asking the place value of the last significant digit. So this is, we're going to use this for question 2. We're going to use this method. We are going to look at the least precise is the largest value of the last significant place value. So I'm now looking for the last one. So again, if I had started, I'm going to double underline. So if I'd started at the first non-zero, I continue to the last non-zero, I pause, I see a decimal point, I go to the end. I start at the first non-zero, I go to the last one, I pause, I look for a decimal point, I see one, I continue to the end. All right, now I look at the place value of the last one. So this place value is it's to the left of the decimal point, so this is the ones place. And this one is the 1, 2, 3, 4th. I could call this the 4th decimal place, or its proper, mathematical name would be 10 hundredths, thousandths, the 10 thousandths place. 4th decimal place is a little bit easier to say. Okay, so which one is larger? This one is the larger place value. So this one is the least precise. And so in this case, I'm going to say the ones place. So again, this would be the method we would use for plus or minus operations. And this would be the method we use for multiply or divide operations. All right, as we practice doing these rounding, now I'm going to do the same thing, but now I'm actually going to do a calculation and round the final answer. I see positive, so if it is plus or minus, I'm going to go for the largest last significant figure. Okay, so in this case, I start at the first, I go to the end, I pause, so the first non-zero, I go to the last non-zero, I pause, see a decimal point, I continue to the end, that would be my last one. In here, I start at the first non-zero, I go to the last non-zero, that would be my last one. So this one is the second decimal place, and this is the 1, 2, 3, 4th decimal place. So this one is the largest place value. So rule, I'm going to round to second decimal place. Okay, now I actually do the operation. 12.0550 plus 9.05 equals 21.105. I should have said I can only do this because they are both in the same unit of kilogram, and that would be my unit. And now I will round it to the second decimal place, and I will get 21.11 kilograms. In the next problem, I'm looking at this one, and I'm seeing this is multiplication, this is multiplication. So for multiplication, I'm going by quantity, smallest quantity of sig figs. So I'm looking here, I have 1, 2, 3. All 3 of these are significant. The multipliers are exact, so that's infinite. And again, this one is a leading zero, it doesn't count. But this first non-zero, last non-zero, and then since there is a decimal point, I do include this one. So this would be 3 sig figs. I guess I can underline these. All right, so my fewest would be, so I'm going to round to 3 sig figs. Now I perform it, 6.21 times 10 to the 3 times 0.15, 931.5, and my units would be meters times meters. Since it's multiplication, I multiply the units as well. And I want to round to 3 sig figs. So this is the first sig fig, second, third. So I want to round at that place. So this is going to go to 932 meters squared. Here I have minus, so I'm going to go with the largest last sig fig. Okay, so this one is here. These are nice. So this one has one first decimal place. This is good to the third decimal place. So this one is larger. So we're going to round to first decimal place. And now I perform 257.2 minus 19.789. My answer is 237.411. Again, because they're both units of centimeters, I'm allowed to do this. I keep the same units. And now I want this rounded to the first decimal place. So this would be 237.4 centimeters. Here I have division. So I'm going to go by quantity sig figs. And I see that this one has 3 sig figs. And this one has 4 sig figs. So we're going to round to 3 sig figs. I complete it on my calculator. And I get 0.1320195. It goes a little further. My units are going to be, can't be simplified, so it's grams per milliliter. And I need this to 3 sig figs. So here would be my first one, my second one, and my third one. So I'm going to round to the third decimal place. So this would become 0.132 grams per milliliter. And I now have this one. This is multiplication and division. So even though there's a combination of multiplication and division, they go by the same rule of quantity of sig figs. So remember, these are exact, so I'm only going to be worried about the prefixes. So 1, 2, 3, 4. This one has 4 sig figs. This one has 2 sig figs. So we're going to round to 2 sig figs. And now I perform it, 7.190 e to the 6 divided by 6.7 e to the 4th. Remember, when you're dividing by two things, either put them in parentheses or use the e-notation, which links them on the calculator, because I need to make sure I'm dividing by both the 6.7 and the 10.4 part. So I get 107.3134. And my units, this art is unitless, so it remains unitless. I want to round to 2 sig figs. So here, here. Notice that because this is 7, I'm going to round up. And it's going to become 110. So I still have 2 sig figs. If there was a case where this would have rounded up, and I had some significant zeros and some non-significant, I would have to put it in scientific notation. Here I have some mixed operation. I have addition, then division. So I need to apply the rounding rules, but I don't actually do the rounding. Ooh, this needs to be grams. That's a typo. So I couldn't add them unless they were the same units. So grams and grams. And I would have, so I would first round the addition to, this one has 1 decimal place, this one has 2 decimal places, 1 decimal place. So I'm going to round to 1 decimal place. So let's do that. 27.5 plus 1.82. Now I don't actually do the rounding, but I will pretend to round by underlining where I would have rounded. So I'm going to consider this the end of the significance, even though I'm going to keep the extra number for the calculation along the way, because if I round and then round again and then round again, I start to get rounding errors from rounding too much. So I'm going to leave it unrounded for the calculation, but I'm going to consider that this is the last significant digit right here. And then I divide it by 100.04 centimeters cubed. and I get 0.2930827. This would be grams per cubic centimeter. Now in this case, my second rule is then round to fewest significant figures. Okay, I'm going to change colors for a minute. So when I consider significant figures, if I consider this one and this one and this one, this has 3 sig figs. Again, I'm not going to count this 2 because I'm saying even though I'm using it for calculation purposes, it's not significant for the rounding. And then here this one have 1, 2, 3, 4, 5 significant figures. So now I'm going to round to 3 sig figs. And when I do that, I get 0.293 grams per cubic centimeter. Similarly, this one is also mixed operation, but first I'm going to do multiplication, division, then adding. So my first rule will be to round to quantity sig fig. So let's perform that first one. So 32.7 times 10 to the 5 divided by 48.533, and I get 67376.83638. And this one has 1, 2, 3, 3 sig figs. This one has 1, 2, 3, 4, 5 sig figs. Remember, multipliers are exact. I can ignore them. So this one should be good to 3 significant figures. 1, 2, 3. Notice again, that's the end of its significance. It's the last significant place is the hundreds place. And then I'm going to, let's look at the units. The grams are going to cancel, and I'm going to have 1 divided by milliliters. But remember, when you're dividing by a fraction, you multiply by the reciprocal of the fraction. So I really get milliliters. And then plus 1594.39 milliliters. So this one, now I'm going to look at the second one, I'm looking at the place value. Then we're going to go by last, the largest last significant figure. So this one is good to the hundreds place, and this one is good to the second decimal place. PD decimal place. All right, anyways, this one is larger, so I'm going to do my calculation. And we get 68971.22638 milliliters, and I'm going to round it to the hundreds place. So this would be 690. That one's significant, 00 milliliters. Note that when I round it, I do need to round up. When I round this up from 89 to 90, this 0 is significant, but these two are not. So the only way to do that, I mean, I'm temporarily doing it with an underline, but the better way to do it is to convert this 6.90 times 10 to the 4 milliliter into scientific notation. A couple more. Note that, again, remember this is sort of implying that I first need to subtract. So I'm going to subtract and then divide by. So again, I'm going to use that in my rounding rules. So I first do 54 minus 56. 54.56 minus 46.34. And I get 8.22. Note that this is good to the second decimal place. This is good to the second decimal place. So this is good to the second decimal place. And on the bottom, 13.4 minus 12.0, 1.4. This is good to the first decimal place. This one's good to the first decimal place. This one should be good to the first decimal place, which it is. Okay, and this is milliliters. So, I mean, the number is, I didn't have to really round anything off anyways. yet. I'm keeping track of it. Now I'm going to do the division. 5.87142 grams per milliliter. But now I'm going by quantity because the last situation was a, now for the division, I'm going to count quantity. So this is 3 sig figs and this is 2 sig figs. So I'm going to do 2 sig figs, and I'm going to round this to 5.9. Similarly, I need to now convert these into appropriate, so I'm going to convert this so it makes it easier. And I'm going to first divide, and when I do the division, I'm going to go by quantity. And when I divide this, I'm going to go by quantity. So in this one, I have 2 sig figs, 3 sig figs. So I'm going to round this one to 2 sig figs. 1, 2, 3, 4, 5 sig figs. 5 sig figs. So I'm going to round this one to 5 sig figs. And I'm going to put this one so I can see the appropriate place value into decimal notation. I want to make a small, since this is negative, I want to make it a small letter, so I'm going to move this number, the decimal place, to the left 2 places, and I get 0.0803 minus 0.00355 divided by 0.0010, and I get 3.55. I'll worry about, so I need 2 sig figs, so this would only be good to there, plus 4200.0 divided by 503.02, 8.34956. I'm not going to go all the way out. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this would end here. So note that now when I'm considering the last one is addition and subtraction. So the rule is the largest last significant figure. So this one is good to the 4th decimal place. This one is good to the 1st decimal place. This is good to the 4th decimal place. So this is my least precise. I'm going to round my answer to 1st decimal place. Okay, now that we've determined the rounding rule, we're going to do the calculation. 0.0803 minus 3.55 plus 8.34956, 4.87986, round to the 1st decimal place, so this becomes 4.9. This is a word problem. Remember, when we're doing our word problems, we really want to situate what do I have, what's my start given, and where's my end point. Okay, it is asking how much what? If I read through, how much should a 1.5 cubic centimeter gold ring weigh? So how much weight? Weight in this class we're going to consider is really asking what is the mass. And what did it give me? It gave me 1.5 cubic centimeter. But I know more. I kind of need to now think about what property is this? What did it really give me? Cubic centimeters is a unit of volume. So I have volume and I want mass. They're not the same thing, so I can't really use traditional dimensional analysis because these are different properties, unless I had a conversion factor that would relate volume and mass. But I can remember that density is the relationship between mass and volume. So I can use the density equation, or this is my plan, or I can use density as a conversion factor. Either way, I need the density. So I was not given here. But another thing it did tell me is it told me that it's gold. I can look up that the density of gold, if I look up in my reference table, it's, double checking, 19.28. 19.28 grams per milliliter. Okay, and also remember that 1 milliliter equals 1 cubic centimeter, so I can replace them. They're equivalent. So that means this also equals 19.28 grams per cubic centimeter. All right, so if I'm going to use the equation, and again, you could go either way, I want the mass. So I want to isolate M, so I'm going to divide both sides by V. I multiply both sides by V, and I get mass equals volume times density. Or I could start with my 1.5 cubic centimeters, and I make a conversion factor that had centimeters cubed in the bottom and grams in the top. Either way, I end up with the same mathematical equation. This one's 1.50 centimeters cubed times 19.28 grams per centimeters cubed. This one is, I would put the 19.28 because that's what's with the grams, and it's implied per 1 cubic centimeters. It's identical math. How I set it up is different, but it's identical math. So 1.50 times 19.28 equals 28.92 grams. I would round this because this has 2 sig figs. I would round my answer. This is multiplication. This has 2 sig figs. This has 4 sig figs. This is exact. So I'm going to round to 2 sig figs, 1, 2, and I would get 29 grams.